All right, let's get going. So let's see. First of all, don't forget to come to class tomorrow. This is it's actually a full week for us, although it's in the wrong order, which is good. If you have labs on Monday, remember labs are actually tomorrow. If for some reason you can't make those labs because of some prior commitment, then just email me. Well, try to go to a different one, but I know there's not too many left for this week tomorrow anyway. But try to do that. For those of you who did the lab so far, not so bad? Not so bad, right? Just a Q lab. In fact, if you're having trouble on the homework assignment, doing the lab solidifies a couple of Q things that you might need to think about. OK? You should be in the middle of homework 3. How's it going? Going all right? Don't raise your hand, but if you haven't started it yet, you're late. Right? If you haven't started it by now, it was actually originally due today, right? And then we've extended it to Sunday. So it's not due until Sunday, but just keep in mind that that's when it's due, and you should already be working on it. I think it's, from the people I've seen, there's a couple little things in there, but it's actually less ripping your hair out kind of bugs than the previous homework assignment. No? I'm getting a no. It's just as many. OK, well, it's there's definitely a few places in there if you haven't like sat down and done it. OK, questions on logistics or anything else before I get going? Should have gotten your homework 2s back unless you handed it in late, and I gave you I allowed you to hand it in late. We haven't quite gotten those yet. OK, any other questions? I just finished lab 2 grading as well. I noticed there were about 10 or 15 people who just didn't do it. So I'm still wondering why you guys aren't doing the labs. Email me if you still want to submit it and give me a reason why you didn't do it. It'll be good. OK, any questions? All right, we're going to do 2 things today. We're going to try to catch up a little bit. We're still behind a bit, but not too bad. We are going to do recursion, and we're going to do it pretty quickly because I know you guys did a bunch of recursion in Comp 11. For those of you who never took Comp 11, hopefully you've seen recursion in other places. If not, like, try to keep up. But if you can't figure it out, go back to the notes and look and come to office hours, and we'll catch you up on that stuff, OK, if you haven't seen too much recursion before. After we do recursion, we're going to start a brand new topic called trees. And did you do trees in Comp 11? No. OK, awesome. So it's brand new. Trees are actually kind of fun. And they're definitely one of the types of data structures where you give it a bunch of information and you get fast behavior out of it. So it's kind of a cool thing. And I think you'll enjoy dealing with trees. And you will see trees the rest of your computer science careers because they kind of crop up in a lot of different places. OK? No pun intended. Trees cropping up. But anyway, OK, so recursion. So this whole lecture has a bunch of little things I put in there that are like little jokes. You ever go to a room that has or a barber shop sometimes or whatever, there's 2 mirrors, one on one side, one on the other, and you when you're 7 or even when you're my age and you still think it's cool, you try to find the last one you can see, right? Because it's goes on and on and on basically forever until the the light can't get small enough to keep bouncing back and forth. This is kind of it's a recursive kind of idea, and recursion is basically this self-referencing, self-referential idea where you kind of redo things. And in our case, we're going to be calling the same function from within the function. So there's some kind of interesting things about that. OK, so we'll get into recursion in a second. I'm going to do Eclipse tip of the day and then recursion. Let's see, Eclipse tip of the day. First things first. Anybody sick of setting up Eclipse and typing that G++ to Clang++? Yeah? Here's what you do. You don't have to write these down now. They're online, but you can look on the slides online. What you're going to do is create 2 what we call links, or soft links, as it turns out, to the actual Clang++ compiler. And you're going to call it G++. And you're going to basically say, hey, when I want G++, you're going to sneakily tell the computer to go get Clang++ instead. Right? So that's the first thing you're going to do. You're going to create these soft links. And like I said, you don't have to write them all down right now. Go back to the notes and type them in correctly. OK? And then in Eclipse, you're going to change what's called your path. Now, the path variable for your program says, where do I check to find where things are? Right? And when you log on to your computer, when you log on to the homework server, your path doesn't include the actual your own like main directory. If you change it and say exactly where your home directory is, you tell Eclipse where it is, it will first look there to find G++, and then you have sneakily told it to go find Clang++, and then it will. So then you never have to do that, and you'll save 10 seconds every time you set up a project. OK? All right. So anyway, you can do that. You can follow that online. And if you have any trouble, let me know. But it makes it a little nicer so you don't have to type that. OK? All right. The Unix tip of the day. Anybody sick of core dumps? Yeah. It turns out I hate these things. Right? Well, I don't hate them because they're kind of interesting. I actually found out that if you have a core dump, you can open that core dump up in GDB, and it will tell you exactly where your program crashed, which is kind of cool. Right? I didn't know that before, but now I looked into it and found that out. So if you want to use it to do that, I think it's just as easy to actually run the program itself in GDB and figure out where or the Eclipse debugger and figure out where your seg fault is that way. But you can actually you can use that if you want. But if you don't want those core files anymore for when your program seg faults, you can actually run this little script that I just created this morning called nocores.sh, and it's in this comp15 public HTML. My laser pointer is dying on me. It's not actually dying. It's weird. I think it's the battery that it can't. It's like overloading the laser pointer. Anyway, comp15 public HTML files nocores.sh, and that will. What that does is it puts a little line into your setup file when you log on that says, "Don't give me any cores." All right, and that's it. Log out of homework and back in, and you shouldn't have any more core dumps. OK, and that'll be nice. So it'll just say, instead of saying abort, program aborted, dumped the core, it'll say program aborted, and that's it. OK, that's kind of nice. All right, questions on that? OK, when you go to Google and type in recursion, this is what comes up. Did you mean recursion? Right? So ever type something into Google and it might just spell it wrong? I don't even spell anymore. If I ever need to know how to spell something, I just type it into Google and it tells me that it should be. But Google asked you what you really meant. Well, because Google is full of nerdy engineers who have a sense of humor, they said, did you mean recursion when you type recursion? And then you click on that, and you go, yeah, I meant recursion. And then it takes you right back to this page and says, did you mean recursion? And then you could click that all day, and Google engineers are laughing. Every time somebody clicks that, they probably get a message. Somebody else clicked it. Anyway, so again, self-referential idea. OK, that's what recursion is all about. Here is the dumbest recursive program you could ever write. OK, this program would work, at least temporarily. And what this says is main is a function. Remember, main's a function. And in main, if you call main, the compiler will gladly say, oh, OK, I've got this function called main. I'll call it for you. And then it would go, 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 and go. And then what would eventually happen? It would crash because of a Stack Overflow, right? What's happening is, you guys talked a little bit about activation records in Comp 11, if you did Comp 11, right? And we kind of did this when we talked about stacks and the stack the other day. When you call a function, the previous function gets stored, and then the next function gets stored, and then the next function gets stored. And this is all on the stack, and you only have so much memory on your stack. And if this is all your program's doing, it's just going to fill up all that memory, and eventually it'll say abort core dump, right? Unless you turned off core dumps. OK, so you wouldn't want to do this. But this is like as basic a recursive program as you could get, even though it wouldn't be very smart to write this. OK, it's a function that calls itself. That's all recursion is. OK, you can actually use this to solve other things, and you can talk about recursion in like a non-computer sciencey way. For instance, if I said, how do I solve a jigsaw puzzle? And you gave me the recursive way to solve a jigsaw puzzle. Here's how I might do it. OK, this would be my whole like how to solve a jigsaw puzzle algorithm. Is the puzzle finished? If it is, stop. Right? Because if you look at the puzzle and it's finished, stop. Right? Last year, my now ex-girlfriend, sadly, and I did a puzzle. We worked on a puzzle for months and months and months. And then finally got to it, and of course there was one piece missing. And we looked for months for that piece and never found it until we moved, and it was under the couch. Anyway, I thought I looked under the couch. But anyway, so basically, we never got past like this algorithm. We kept going on this. Not the reason we broke up, for what it's worth, but a much longer story there. Is the puzzle finished? Stop. OK, this is what's called our base case. All right, and then what you do is you find a correct puzzle piece and you place it in the puzzle. Now, this is a little it's a little simplified, right? I mean, that's kind of the hard part, right? In fact, I've actually thought of this a number of times, especially when we were working on this horrible puzzle. Why doesn't somebody create an iPhone app to take a picture of the puzzle pieces and then using some sort of computer vision, like figure out where the pieces go and then tell you to like move this one here and move this one here and move this one here, right? It's probably like really intense to write that, but I totally want to do it someday. And if you ever want to try it, let me know. We'll set up a little group and we'll like try to hack away at it. It might take a couple months, but it would be kind of fun, wouldn't it? You know, the puzzle piece solver. You could probably charge $100 on the iPhone store, right? Well, probably not, but you know, depends how desperate you are, I guess. So anyway, so find a correct puzzle piece and place it. That's the step. And then solve the puzzle, right? Because that means you've done a step. You've gone in the direction of solving the puzzle. And then you go back and you say, look, is it finished yet? If so, stop. If not, find a correct puzzle piece and place it. Solve the puzzle. That's a recursive solution, right? You just keep doing the same overall algorithm time and time again. OK? That's recursion. OK? In general, we want to solve recursion the following way. And again, I know a lot of this is review. For what it's worth, seeing recursion a number of times is helpful. Like the first couple times you see it, you're like, I don't really get it. And then, but I think you guys did a lot in Comp 11 on that for those who took it. And but seeing it again a review is always a good thing. So you check for this thing called the base case. That means that whatever problem you're trying to solve has been solved. OK? You check for the base case. Occasionally, you can check for the base case at the end, but normally we check for the base case straight off the top. OK? Check for this base case, saying, are we done? And then you've solved the problem and you stop. OK? Sometimes we actually return some result. Sometimes we just are done with it. If you're printing out a bunch of things, you might not need to return anything. Otherwise, you need to return something. And if you're returning a result, sometimes you need to propagate what you're returning through all the other functions that get called. OK, we'll see some examples of that today, and you'll see how that works. OK, if you're not done with the problem, then you work towards the base case. In other words, solves part of the problem that you're trying to solve, and then recursively call your own function again with some updated data, which allows you to check if you're done solving it. OK, that's the idea of recursion. OK, why do we use recursion over looping? The answer is, honestly, beauty. Like, that's really the answer. So many recursive solutions are kind of inherently beautiful in the sense that they are short and they are very easy to state. That doesn't mean that they're necessarily the best way to go about doing things. OK, Stack Overflows are like a huge reason why you don't want to do this. OK, sometimes, and we'll see an example later, the recursive algorithm might be beautiful, but it'd be really dumb to do it that way because it's really inefficient. OK, so there are some good reasons to do it. And in fact, many computer languages, well, the original computer languages that people created, like Fortran, I don't know if you've even heard of Fortran before, but Fortran did not originally have the ability to do recursion at all. And then eventually people started writing other languages, and they had these big discussions about, should we even add this? Is it worth adding, or should we not allow it? And it was a big argument, I guess, for a while. And then finally, people said, yeah, let's add it. And then now we have recursion. And I think people think it's probably a good idea that it's allowed. But it wasn't always the case. OK? All right. So let's say we wanted to count down. I know you guys have talked about this before, but let's review this. If we want to count down from some number n down to 0, including 0, OK? First we say, is n less than 0? That's our base case, right? If I said count down to 0 from -7, you'd go, I'm done, right? Because you're already past it. If it's 0, we're done. Otherwise, you say the number. In other words, count down from 10. OK, 10 is not less than 0, 10, right? And then you count down again. In other words, do the same, start over from n minus 1. Same thing. If n minus 1 is your new value of n, if that's less than 0, then you stop. If it's not, say the number and then count down. Make sense? Fairly straightforward. Let me show you the example. Yeah, Nathan.
Is this an example where the recursive solution is cool but impractical?
Is this one of the ones where it's cool but impractical? Kind of, because a loop is so easy to write for this. Like really counting down with a loop is like so easy. In fact, many compilers these days could turn this recursive program into a loop. It's smart enough to say, oh, I can do that in a loop and it's easier. So it might do it that way instead of calling the function. But we won't go into those details. Okay, you will when you get into programming languages class. All right, so here's what happens. OK, we have the function count down. It takes the number that we're on, and it does exactly what we said. If count is less than 0, return, we're done. Otherwise, print out the number that we're on, and then count down, count minus 1. OK, for count down 4, if count is less than 0, it's not. Print out 4 and a new line, and then count down from 3. Whoop. If count is less than, now count is 3, so 3 is not less than 0, print 3, et cetera, down to 0. You get how that works? OK, not hard stuff. What if we wanted to count up using this recursion? What's nice about counting down is that we've got a base case we're always going to head to. We're always heading to 0. Right? If we're counting up, is there something that we're counting up to? Yeah, I mean, unless given this little putting in what number we're on, you have no idea when to stop, right? And you would if you put anything there, let's say you put 100. OK, well, you're always stopping at 100. What if you want to count up to 1,000, right? Then this would have to change. All right, and then this same thing too. You're going up to what? What are you going up to? You just don't know. Right? So we're in trouble here. There are many solutions to this problem, one of which is what I would call the ugly solution, but it would work. If you know you have to go up to some value, why don't you just give that value, say that value when you do the recursive function, and then just pass that value in every single time you call every recursion during the function or during the program, right? Say we're going to go from 0 to 10. We could put we would count up from 0 to 10, and we would basically have our base case be if count is 10 plus 1, don't print it, right? We're done. And now we've got max, and we have to pass max through every single time. OK? I call this the ugly solution because it takes 2 parameters, first of all, although this is a little bit more useful, right? What can you do now that you couldn't do before? You could start from a negative number. You could go up to some number. You could actually start from a positive number. Right? If you wanted to count from 10 to 20, you could do that. You could say count up 10, 20, and it would do it. Right? So this is actually slightly more useful. All right? And you wouldn't call it count up. Maybe you'd kind of say count between or numbers in or something, whatever. Right? And you could do that. There is another solution, though. OK? And you guys may have talked about this in Comp 11. See if you can either drag it out of your brain or figure it out again. A slightly different and, I would say, much more beautiful solution can be done with this program changing one thing about this program and not count down to count up. That doesn't count. If you're counting up, let's say you're trying to count up, what's one thing you could change in here? Now, I want you to do this. Take 2 minutes, talk to your neighbor about this, and see if you can figure it out. If you can't, that's all right. But think through a couple things, and then we'll talk about it. Talk to your neighbor about it. Amanda, what do you think? What would that do? Countdown count plus 1, that would probably work, except you'd still have this issue of what is your base case, right?
So you're counting up to some number.
You are. You have to count up to some number. And all you have to do is change one thing about this, and it'll actually work. If you can't figure it out, that's all right. This is a little tricky. But it's actually really clever. When you see it, you'll go, oh, that is clever. Or you'll say, stop saying it's clever. It's not that interesting. I think you'll think it's clever. OK, does anybody think they have it? If not, that's all right. Somebody happened to get it in the other class. Just I think they might have figured it out. Yeah, what do you think?
You can switch the order of countdown in the cout statement.
Ah, if you swap these two statements, okay, if you swap those two statements, why is that going to work?
Because that way the previous, how do I say this? That way the previous call of the function is still running as you go through until you count down. The program basically counts down to 0, but all the previous ones are still running until you hit below 0. You return back to the next one up. It's
Yeah.
0, then it goes back to the next one.
Let's walk through this a little bit, because this is really important to understand this. When this count down function, before we change anything, when this count down function gets to this line, it prints it out, the number, and then it goes to this line and does the recursive call. If, on the other hand, we swapped it, let's see, if we swapped it, oh, it doesn't have it swapped, actually. I thought it actually had it swapped. If it swapped it, oh, no, it did. Sorry, it does have it swapped now. If it calls count up first, when does it get a chance to print the number? Only once the base case is passed way down the line. Let's just walk through this for a second. Let's look at this one and say count up from 0. I'll abbreviate CU. Count up from 0. OK? If we count up from 0, all right, I'm sorry, count up to 10, rather. I lied to you. Count up to 10. If we count up to 10, no, let's make it 4 so we don't stay here all day. All right, count up to 4. OK? The program says is count less than 0. It's not. All right? So what do we do next? This immediately calls what? Count up 3. This one checks if it's 0 or if it's less than 0 and calls count up 2. And have we printed anything yet? No. And then that one checks if it's 0, and this one calls count up 1. And then this one calls count up 0. Now, what does count up 0 do? Calls count up -1. Calls count up -1. And count up -1 does what? It says, I'm done. Count up -1 returns to count up 0. What was the last thing count up 0 did? Called count up 1. So what's it going to do right now? It's going to see out itself. And count up 0 see outs 0. So we get 0. And then that returns, because it ends the function, and it returns to the thing that called it, which was count up 1. And count up 1 just finished calling count up 0, so it now prints 1. And then the same thing happens for here to see out 2, and you get 2, and then you get 3, and then you get 4. And what called count up 4? Let's pretend that's a 4. Main did, so count up 4 ends, goes back to main, which ends, and we're done. OK? Really key idea that this actually happens this way. Yeah?
Why is that more efficient than the other way?
Why? It's not necessarily more efficient, although it's less things to do, actually, right? And well, you don't have to have two parameters, first of all. That's really the big one. But otherwise, it's the same number of lines as the count down recursively, and it's kind of clever. And the reason it's clever is because you don't actually print until the end, so everything has to happen in the reverse order. Okay? Remember, recursion is a stack-based idea. Okay? So it's basically first in, last out, or last in, first out. Okay? And in a last in, first out program, or I guess algorithm, right, it depends on when the out happens as to which order you get it in. Right? So you're still counting down inside the program, but you're waiting until everybody's almost returned to start printing out. OK? So key idea here to make sure you get this, get this idea. OK? Other questions on this one? All right. So I think that's an interesting one. It's clever, right? And it's kind of interesting. There are lots of other things that we can do recursively. OK? We'll look at a couple different functions recursively. Some of these are better than others. Most of them you could write with a loop much easier than doing it recursively, but at least it shows you a little bit about this. OK? All right. First thing we're going to look at is the power function. OK? In other words, raising a number to the power, a power. OK? If you have b raised to the n, what does that actually mean? It means b0 times b1 times dot, 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 bn. Correct? OK, or I guess it would be n minus 1 technically, right? It'd be n times altogether. OK? B times that. Well, this is actually a really easy recursive function to think about because really, like let's say you have, I don't know, 4 cubed, right? 4 cubed really means 4 times 4 squared, which really means 4 times 4 times 4 to the 1, which really means 4 times 4 times 4, can't draw it, times 4 times 4 to the 0. Right? Isn't that what it really means? Right? And I guess the 4 to the 0 is not going to matter too much, although it will in our to get it right. OK? So to do the factorial problem, or sorry, the recursion problem, it's pretty easy. OK? You're basically saying, look, if you've gotten below 0, stop. OK? Otherwise, return b times the power of b n minus 1, which is exactly what this is doing. 4 cubed is really 4 times 4 squared, which is really 4 times 4 times 4 to the 1, which is really 4 times 4 times 4 to the 0, and you're done. OK, you see how that's recursive? And this is the one where we're actually returning something. OK, this says return b times the power of b minus 1. Okay. Questions on that one? This one's a little bit more advanced, but not much, right? And again, you would probably just do this one. Let's see. Do I have this one? No, I don't have the actual for loop, but it's a pretty darn easy for loop. OK? All right. The next one that we're going to look at, very similar, the factorial function. Right? And remember, factorial is a number times the number minus 1 times the number minus 2 times the number minus 3. Look how nice and beautiful and simple it is in the recursive form. Right? You basically say, give me a number. If it's less than or equal to 1, return 1, because 1 factorial is 1. Right? And 0 factorial, I guess, is also 1. Right? And then you return n times the factorial of n minus 1. Right? Which gives you, and if you did factorial of 5, it would be 5 times factorial of 4, which is 5 times factorial of 4 times factorial of 3, et cetera, et cetera. OK, very beautiful solution. Now, the iterative solution is not much different. It's just a little bit longer. Right? You have to keep a temporary result around, which is kind of important in this case. Right? Same idea. We're done if you're less than or equal to 1. And otherwise, you have to do a for loop. And you just go from n down to 1, subtract 1 each time, and just multiply the temp result times whatever I currently is. That's it. And then you're done there. So not too much longer, but in terms of beauty, this one actually, I would say, wins out. Because it's simple. It's very mathy in the sense of, hey, this is all you're doing. Right? And it is really a recursive idea. OK? Questions on that one? OK. So that's recursion there. Yeah? That's a good question. Which is faster? Well, some compilers will turn this into this. Right? So in this case, this one is probably faster because this one has all that overhead of calling a function, which means save everything that's here, call the function. When it returns, undo the, restore everything. So this is probably a little bit slower. And this one has the problem of ending up with a Stack Overflow, too, because you've got all those recursive calls. If you're doing factorials, you're probably not doing huge factorials. They get pretty big pretty fast. But you probably still would want to do it this way if you were really doing it. Yeah, good question. All right, anybody else? OK, let's look at another one. This one I like a lot, the Fibonacci sequence. Who remembers from math class what the Fibonacci sequence is? A couple people? Who's never seen it before? Oh, OK, good. You just don't remember. Or you don't want to admit it. OK, what is it? What is the Fibonacci sequence?
This is a sequence of numbers that build upon the one behind it, that build upon by adding the two behind it.
OK, it's the sequence of numbers that build by adding the two behind it, which means that you have to start it off with something.
0 and 1.
OK, yeah. So the Fibonacci sequence starts, and it goes 0 and then 1. And then you add those two, and you get the next one. So it's 0, 1, 1. And you add the previous two, and you get 2. And then you add the previous two, and you get 3. And so far, it looks kind of boring. But then it all of a sudden goes, oh, now to 5, and then 8, et cetera. OK? We call this the Fibonacci of 0, 1, 2, 3, 4, 5, and 6. OK? That's how it works. Fibonacci of 0 is 0. Fibonacci of 1 is 1. Fibonacci of 2 is also 1. Fibonacci of 3 is 2, et cetera. This shows up in biology a lot. I guess nature, there's a lot of Fibonacci sequences and so forth. But it's a nice little sequence. Doing it recursively is very easy, and many would argue very beautiful, right? You have your base cases here. Basically, if it's 0, you better return 0. If it's 1, you better return 1. That's going to handle your first two base cases here. Otherwise, what do you return? You return Fibonacci of n minus 1 plus Fibonacci of n minus 2. And that's like beautiful, right? Mathematicians would love this. Computer scientists hate this. OK? Why do computer scientists hate this? A couple of other people. Why do you think it's slow?
Because it's calling the function twice for every single function call, so it's quadratic behavior.
Not even quadratic. Worse than that. Exponential behavior. Let's just take an example. OK? I'm not sure my board's big enough, but let's take an example. Let's do the Fibonacci of 4, which should give us 3, right? OK? Fibonacci of 4. If we plug that into here, I'll abbreviate with fib, right? Fib of 4, OK, calls what? It calls fib of 3 and fib of 2. Fib of 3 calls what? Fib of 2 and fib of 1, the plus there. And fib of 2 calls fib of 1 and fib of 0. And it's returning all this each time. OK, fib of 2, right? Fib of 1 and fib of 0. And then fib of 1 does what? Returns 1. And fib of 0 returns 0. OK, and then fib of 1 we said is 1 again, and fib of 0 is 0. OK, and then did I miss one here?
There's a 1 in the middle. Fib 1.
Right here. Oh, you're right. And that one returns 1 as well, right? OK, so if you add all these up, as it turns out, if you add all these up, 1 plus 1 plus 1 gives you 3, which is what we're looking for. But look at how much this program exploded, right? It went and exploded out like that. Notice a couple other things. Not only did it explode, which is necessary in some problems. Remember, we talked about there are some exponential problems which nothing you can do about them. They happen to be exponential. But look at this one. Fib 2 gets called here and here. And that answer is going to be the same, isn't it? Like the answer to fib 2 is going to be the same no matter how many times you call it, right? Fib 1 gets called here, here, and here. Fib 0 gets called there. How much more work are we doing when we don't actually need to, right? Exponential more work in that sense. So not a good idea to do it this way, all right? Yes, it's beautiful. Yes, mathematicians love it. But from a computer science perspective, this is a terrible thing to do because you've blown up your problem, right? You've solved it. You've solved a piece of it by giving me 2 more things to do, right? Which is exponential behavior. Not a good thing. OK? All right, so what could we do instead? Remember the ugly count up function, where I passed along some information each time. In other words, I passed what I was going up to each time. We're going to do the same kind of idea for Fibonacci. What we're going to do is we're going to create this function called Fib Helper. Now, the reason we call Fib Helper is because it makes it so that we can still have our Fibonacci function that just takes one number. We want this. We like this idea. We like saying to the user, give me a number, I'll give you Fibonacci. We don't want to tell the user, hey, you're going to have to do 3 things when you call this function. Just deal with it. We don't want to say that, right? We want to say, call one thing, and we'll do all the rest of the work. Here's what we end up doing. We have this Fib Helper function, and it takes in the number that we're at, and it also takes the previous number and it is the second, the second previous number and the previous number. Okay? That's what it takes in, okay, as its arguments. So what you do when you call Fibonacci on a number, if it's 0, we return 0. If it's not 0, we call Fib Helper with the number, and what we call seed it with the first 2 Fibonacci numbers, 0 and 1. Okay? Let's walk through what this does for Fib 4. Okay? For Fib 4, what does Fib 4 call? Fibonacci 4 calls Fib Helper, I'll abbreviate FH, Fib Helper 4, 0, 1. Right? OK. And then Fib Helper 401 calls what? Let's think. It goes, is n equal to 0? No, it's 4. So then it calls Fib Helper, and it calls, let's see, it calls n. Right? Oh, sorry, I'm over here. Sorry, I lied. If it's not 1, return P1, which is not. Return Fib Helper n minus 1, which is 3, and then P1, which was the second one. So what gets put here? 1. And then the first plus the second here, 0th plus the first one here. 1. Notice we have passed along the 2 things that we don't want to recreate. We're doing it and passing it along and saying, use what we created. Don't recall this all the time, right? Fib Helper 311 calls what? Fib Helper 2. P1 goes over here, 1, and then 2. And guess what? 1 and 2 are the next 2 Fibonacci numbers. Fib Helper 212 calls Fib Helper 1, 2, because this one goes here, 3. And then Fib Helper, let's see, Fib Helper 1, 2, 3 calls, returns, it doesn't, it returns what? P1, which is this one. So it returns 3. And then that returns this one, and this one returns this one. So 3 goes all the way up to here, which returns 3. And guess what? 3 is Fibonacci 4. So you see how that works? Much nicer in the sense of we're not doing anything exponential now, and we are passing along some more information. Okay? The downside to this is you do need another function for this, and you're passing along some values. But it just saves you all that extra time recalculating things. Okay? Don't recalculate if you don't need to. All right? Kind of neat. Let's look at, I won't go over this one too much. Greatest common divisor. The greatest common divisor, if you'll remember from like 5th grade or 4th grade or whenever you did it, is you take 2 numbers and you figure out what the largest number that goes evenly into both numbers is. Okay? There's a brute force method to do this. If you have 2 numbers, let's say you have 27 and you have, I don't know, what's one that might work? 27 and 18 or something, right? If you have 27 and 18, okay, the brute force method to figure out which one goes into which would be what? What can you think? Somebody has an answer in a little bit. Winona, what do you think?
You separate them into their factors and then
Oh, that's the way you do it like in math class. I'm saying the way a dumb computer would do it. Yeah. Try everything from what? Let's not go up. Let's go down because we want to find the biggest one. Right? So we want to know when to stop. So if we go down, what happens, Alexander?
Start from the lesser number.
Start from the lesser number. If we start from the greater one, we're just going to waste more time. But we could just start from 18 and say, does 18 go into 27 and 18?
Nope.
No. Does what? What are we going to check next? 17. Does 17 go into both? No. What are we going to have to get down to until it works? 9, right? You'll eventually get 17, 16, 15, 14, 13, 12 down to 9. 9 will go into both, and you'll be done with it. That's a pretty good recursion type program, right? And here it is. OK? Here's what you're going to start out with. You're going to start out with your greatest common divisor. And you're going to have a helper function to do this, where it calls the first number, the second number, and the second number again. And then it just does that. It says, look, if the mod gives you the remainder, right? So if the number by our guess, our second number is now our guess. If the number mod our guess is 0, meaning it goes in evenly, and the other number mod our guess goes in evenly, return the guess because we're right. OK? Else, return try divisor, the first number, the second number, and then one less. Right? That is a recursive function that will work just fine. It is the brute force method, right? Which is not particularly nice. Now, unfortunately, I don't have too much time to go into the details of the really, really cool solution. There's a guy named Euclid. Worked about 200 BC, right? About 2,200 years ago, right? And Euclid's one of the most brilliant mathematicians ever. He's got a whole geometry named after him. Just figured out that what you can do instead of doing this whole business of brute forcing it, you can actually first check if the number is if your number you've gotten down to is 0 and return the other one. Okay, meaning that you've arrived at your solution. Otherwise, if you call GCD on the second number and the first number mod the second number, it will actually give you basically the remainder of those two, and then it will walk down that way. Instead of brute force, it goes down by the remainder of the division, and it's super duper fast. OK? Yeah?
Does that only work if x is greater than y, or does it work in either way?
Let's try it. Let's see. It's a good question. Does it work? The question was, does it work only if x is greater than y? Let's just try it, right? So let's see. Let's try two numbers. I don't know, GCD of 13 and 5. OK, let's try this and see if it works out. GCD of 13 and 5. OK, is 5 equal to 0? No, so we don't return that. So return GCD of what? This is going to call return GCD of 5 and 13 mod 5. OK, what's the remainder when we divide 13 by 5? 3, right? Because it goes in twice with 3 remainder. OK, and then this is going to call what? That's not 0. So it's going to call GCD of 3 and 5 mod 3 is 2, because it goes in once, a 2 remainder. OK, and then this calls GCD of 2 and 1. All right, and then this calls of 1 and 2 mod 1 gives you 0, because 2 divided by 1 is 2 with no remainders, 0. This returns what? 1, which goes back up the chain. And the greatest common denominator of these two is indeed 1, right? Guess I should have picked 15 or something, or something else that didn't work out. But that works fine. Let's try it the other way around. Let's try it with GCD of 5 and 13. What does that call? It's not 0, so it calls 13. 5 mod 13. 5 divided by 13, 0 remainder. What do we get back? Right? So it does. It's one extra step. But yeah, it works perfectly well with the other one. Yeah, because this is exactly what we started with in the previous one. OK? So yeah, so this works great. And it's actually pretty fast compared to the other one. If you want to look here, you can see some of the math behind why this works. It's actually very clever. And you can tell why Euclid was kind of a smart dude. OK? Questions on that one? OK, sorry I don't have more time to go through the math on that, but it's on there. Oops, there we go. The last one I wanted to show you was this one called is palindrome? What's a palindrome? Yeah. Hannah.
When the letters are the same forwards and backwards.
Letters are the same forwards and backwards. Can you give me an example?
Like my name. Yeah.
Your name. H-A-N-N-A-H. There we go. When did you first learn that?
I was about 4 years old.
When you're about 4 years old. Nice. OK, that's cute. OK, so if it's backwards and forwards is the same, let's do it. Now, this is actually a pretty easy thing to do recursively, although there's lots of comments in here. But basically, all you have to do to figure out if something's recursive is what? First thing you have to do is compare what? If the what? If the ends are the same, right? So if the h's are the same, then we're good. And what do we need to check next? What's left, right? And isn't that recursion? Because you can say, check the ends, and then do the same thing for the one without the end two values. And then if the a and the a are the same, right, then you check the ones in the middle. And you stop when you get either, well, when you get a length of your string less than 2. Because if it's only 1 character long, every 1 character word is a palindrome, right? Because a is backwards a, and it's the same. And a 0 length string is also a palindrome, right? And you can do that. So recursively, it's pretty easy. Base case is check if it's less than 2, return true. And then otherwise, we're going to basically, this is stripping all this stuff here is just basically saying, give me the rest of the string besides the ends, and recurse. Return is palindrome the new string. And that's it. OK, kind of a neat one. You can use it for strings, too. And that's that. Questions on that? All right. So that's the whirlwind tour of recursion. OK? There's some reading on here. You can definitely go and look up some of the other things. Again, if you're like, oh, that was way too much, then see me or go over the slides again, and you'll start to get it. But it does take a couple of times to pick it up. OK? Any other questions on that? All right. Let us blast into the next topic, which is trees. OK? I put this up here for the reason that this is actually a really cool looking tree. Because if you'll notice, every one of the branches does what? It splits in 2, right? This is actually what I would call an upside down binary tree, right? And we'll get into what all that means in a few minutes. But basically, if you look at this and you flip it upside down, you'll see what most of the trees that we are going to study look like. Not the first ones. Actually, we're going to study non-binary trees for a few minutes. Then we're going to go into those. OK? But trees, like I said, you will see them through the rest of your computer science career. They show up a lot. And they're relatively easy to conceive of. Dealing with some of the issues with them are a little tricky, but we will get into all of that. OK? All right. Let's see. Another Unix tip of the day. Oh, comments on late work. I think I covered most of that before, but I just want to reiterate a couple things. OK. The scp command, right? If you want to copy files from your computer to the homework server or from the homework server to your computer, you can use this command called scp. I've showed some of you guys this. It's pretty easy to use, although it seems like it's kind of long. All it does is allows you to copy between servers or your computer, right? scp abcd says copy file A, B, and C to D, whatever that D is. OK, if you have 2 things that you want to copy, let's say you wanted to copy main.cpp from your computer to the homework server. scp main.cpp. And then you want to do it to the homework server. Well, you got to tell the homework server who you are and what it is, right? So you have to say, I would say, cgreg at homework.cs.tufts.edu, right? And then you put a colon, and that colon is really important. That colon says, that's a server. Otherwise, it just copies it to a local file, and then you have no idea what's going on. But if the colon says that's a server, and then you put where the actual program, where you want to actually put it. So you might say something like desktop/comp15/HW3 or something like that. OK? That would copy. I know it's long, But that would copy from your own main on your computer to your account at the homework server into desktop/com15/homework3. OK? If you want to do it the opposite way, you just flip these. If you want to copy main.cpp to your local folder, you would do scp cgray at homework blah 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 desktop.com15 homework3/main.cpp, and then you could put period, or you could put main.cpp, and it would copy it to where you locally are on your computer. OK? That's one way to do it. I use SCP all the time these days. You could also just get an SFTP program like CyberDuck or some of the other ones. I love CyberDuck. It's got a fun icon. Let's see where it is. Oh, it's down here. Can you see the little duck down there? Whoops. And now it's going to open up and try to do its thing. Anyway, let's see. If we do about, maybe it'll give you the duck again. There it is. Kind of cute. So that's why I keep it on my computer. OK. All right, that's why. All right. Questions on that? OK. Quick on late work. I think I said this before. I don't care if you guys provide a couple hours late. Don't worry about that. If you're going to provide something more than a day late, or like more than like a few hours late, like into the next morning, just email me and do it before either the regular deadline or before like I wake up. In other words, do it at some point like before it's going to look late to me. That makes sense? That's all I really care about. OK? My general late penalty is if I don't hear from you prior to the due date, you get a 0. Have I ever given a 0 because of that? Maybe once or twice. But I mean, I generally don't. But I just really like you to hear from you beforehand. That's all. OK? And there's no TAs Friday nights. They're out having fun while you're working on homework. OK? That's it. Questions on that? OK. All right. So trees. All right. We have so far covered a number of different types of data structures. Right? Really, we've only covered 2. We've covered arrays and linked lists. Both of those suffer from this idea of, they suffer from one of 2 things. Either they take linear behavior, which we don't love. Not terrible, but we don't love it. OK? Or the only way you're going to get constant behavior is if you limit them to, say, a queue behavior or a stack or something like that. OK? So they're not that great. If we change our linked list to be this thing called a tree, OK, we actually make it so that we give the tree more, we give the data structure itself more information so that we can actually have better performance, as it turns out. OK? You break the problem into either halves or quarters or thirds or whatever. You're breaking the problem down by creating this structure, by giving it extra information. OK? So we're going to look at a couple things today. We're going to look at how trees can implement a file system. So as it turns out, the file system on your computer is basically a tree, as it turns out. OK? We're going to talk about how trees can evaluate arithmetic expressions. We're not going to talk about these last 2 things. We're going to jump into these things called binary trees, and we'll wait on these for a little bit later. But those are the things we're going to talk about when we talk about trees. OK? What is this thing called a tree? Well, this is the mathy kind of computer sciencey description. Tree is a collection of nodes. Now, you already know what nodes are because your linked lists have nodes. It's a collection of nodes which could be empty. You can have a tree which has no nodes in it. If it's not empty, there is one node called the root of the tree. Notice it's keeping this like real biological tree analogy going. We're actually going to mix analogies in a little bit. You'll see. And then 0 or more non-empty subtrees whose roots are connected by an edge from the root. A directed edge, as it turns out, but that's because you can only go one direct. Well, actually, it's not necessarily directed, as it turns out. But don't worry about that. We'll get to what that means later. All of those words mean this. OK? Here's an example tree. Sorry, some of these red is hard to read. I'll read out whenever it says something in red. This is what a tree looks like. OK? You have the root here, which has a bunch of edges which go to other nodes, which themselves can be considered little trees, which have edges to other subtrees. OK? We have to get a couple of terms down, first of all. OK? This is called the root, as we said. OK? B happens to be called a child of A. Now, that's more of like the family tree kind of analogy, right? Like you've all heard of family trees, right? And family trees are not necessarily trees because you can get weird things happening like cousins marrying cousins and all that, and things get weird, right? Just go look at the history of the British royal family and you'll find out it's not a real tree. But basically we say that, look, if you've got a node and below it is another node, that is the child of the node, which means that A is what to B? The parent of B, right? OK? So we can do that. We can say, for instance, F is a child of A and a parent to both K, L, and M, to all K, L, and M. OK, a couple of terms there. OK. Note about this, there are n nodes and n minus 1 edges. Can anyone tell me why that's the case in like a one-liner? Yeah. Chanel. There's no edges that go down to the root. But let's think of it. Every node except the root has a parent. Think of it that way, right? Everybody has a parent except the node, or except the root. Okay? And by the way, can you see how this is like a little bit like a tree upside down? Like this is a root, but then it's kind of everybody going upwards like that. Okay? All right. So we're going to mix metaphors or mix analogies again. Nodes with no children are called leaves. Now this is back to the biological tree, right? These are all leaves because they do not have any children. Okay? All right? All the red ones there are leaves. Nodes with the same parent are called siblings. Let's go back to the family tree analogy, right? Siblings. Okay? Who's an only, or who's an older child here, or an only child? Like the oldest or an only? Yeah. Who's the younger child? Yeah, the younger children. You guys ever notice that there's like way fewer pictures of you than there are of your older siblings? I asked, so my sister, I'm an oldest, and my sister's younger than me, and she always gets mad. She's like, Mom, there's no pictures of me around. My mom's like, yeah, we just got a little sick of taking pictures after Chris is around, So, yeah. Anyway, siblings. I and J happen to be siblings because they have the same parent. OK? All right. We can define a path from a parent to its children. OK? Path just says, how do you get from a parent to its children? Or you could call this a grandchild or a great-grandchild. We don't want to go overboard with those terms, but you could do that, right? A path from A to O goes A, E, J, O. OK? And the length of that path is how many jumps it took to get from A to O. OK? Took 1, 2, 3 jumps to go from A to O. That's the length. OK? Yeah, Hannah.
Can you explain what edges are?
Edges are the lines between them. That's all they are. They're just the connections between them. Yeah. OK. So the depth of a node is the length from the root. In other words, the depth of J is how many hops does it take to get from the root to J? 1, 2. The depth of J is 2. What's the depth of the root? 0, right? The height of a node is the longest path from the node to a leaf. Now, various books, in fact, I think your textbook would actually say something slightly different. We're going to use this. We're going to use this way of thinking about it. The height of a node is the longest path from the node to the leaf. So the height of F is 1, because it takes 1 to get to a leaf, and that's the greatest distance. OK, the longest path. Let's look at the height of A. You could get to a leaf by going A, G, N, which would be a height of 2. But there's a longer way. A, E, J, P, or A, E, J, O takes 1, 2, 3. So the height is actually down to the bottommost level. OK? The reason we care about that is because when we're talking about asymptotic complexity and things, we want to know what the maximum distance is. OK? All right, that's the height. OK, the height of a tree is the height of the root. OK, and again, your book might say that it's 1 less than that. We're going to just go with this one. The height of the root in this case is 1, 2, 3. That's the height of the tree. OK? All right. Nodes can have ancestors and descendants, right? Back to the family tree one. Ancestors and descendants, right? E is an ancestor of P and a descendant of A. And it basically is, can you reach that node going down? Then you're an ancestor. Going up, then you are a descendant. OK? Pretty simple. K, descendant of F. No ancestor, not an ancestor of anybody. OK? All right. How do we actually implement trees? Now, this is like getting back into the computer science-y part of it. OK? We could have a link, or have each node link to each child. In other words, let's say we took our node from a linked list, right? We have our node from a linked list. And we could, let's go down, because we kind of do sometimes. Let's say we have our node, and we have our data, and then we have a link to one child, and a link to another child, a link to another child, a link to another child. You could store all those links in there. But there's some kind of inherent problems with that. It doesn't scale very well. First of all, you have no idea, or the number of children can vary greatly. You can have no children, or you can have 1 million children. Right? So you can't really say how big this is going to be. You also don't know how many children you're going to have in advance, which I guess is true in real life too, right? But you don't. I mean, I guess you don't. The number of children is not known in advance, so you've got an issue of saying how many nodes do we put here? We can't just make it an array and say that's how many we're going to have, because it's going to be a little more subtle than that. So what we can do is we can do something sneaky like this. This is not necessarily anything you'll see again. Maybe you will, maybe you won't. But this is one way of doing it. You could have a tree node. You could have the data, and then you could say, look, the first child gets a link, and the next sibling also gets a link. If you do this, right, then you just make these into little linked lists, and everything works out all right. Because your first child goes to another object node, which may have a first child or it may have siblings, and your next sibling does like this. So let's look at A. A has no next siblings, because it's the root. However, A has a first child, E. E has a next sibling, F. E also has a first child, I. And you see how the whole tree is actually represented that way? You can represent any tree like this. Yeah?
You're just making a binary tree.
We're not making a binary tree. Here's why we're not making a binary tree. Because, and we haven't even talked about what binary trees are, but because, look, F has K, L, and M are all children of F. OK, so it's not binary anymore. There's actually, it's got 3 children. So there's and A only has 1 child, et cetera. OK, so it's not quite. We'll get to what that means in a bit. OK, that's one way of doing it. This is a pretty asymmetrical view, which is not necessarily beautiful. I don't like these asymmetrical things if we can help it. But sometimes we have to deal with this. OK, what we can do with this is how we can actually model a file system. Files, think about your file system. When you go onto when you log into the homework server, you've got a bunch of files and you've got a bunch of directories. Let's label all the directories with a little star, right? And we'll label the files just as a letter. So A, which is like when you log in, that's where you are. You're at their home folder. And it has 3 files in it. All 3 happen to be folders, I should say. All 3 are folders, E, F, and G. Right? And so you'd say A's, what did we say it was? It was first child is E. And then E has a first sibling, and F has first sibling, and that's like the first row there. And then E has 2 files in it. One's I and one's J. J happens to be a folder, which has 2 files in it, O and P. See how that works? Again, it's kind of asymmetrical, but it'll actually get to the whole tree. OK? What you can do with this, and this is a little bit of code here, but what you can do is you can print it recursively. Trees are awesome for recursion. Everything works out really well with recursion. OK? And because trees aren't necessarily that deep, you actually generally get very good behavior and don't have to worry about things like stack overflows. All this code is basically doing is it's saying, look, here's our base case. If our node is null, just return. Otherwise, print the node and the depth of the node. In other words, the depth will tell you will basically say how far over are you going to print like the next level. When you see what it prints out, you'll see what it means. Then it says, look, call list all again on the first child, my first child, at a depth of 1 more than my depth. Because A is depth like 0, and E is depth 1, and I is depth 2, and so forth. Okay? And then it also goes and has to print all the siblings as well. Okay? You can go on your own and look at like what this does at your leisure, but here's what it actually prints out. A has 3 children, E, F, and G. E, F, and G. Notice how A is tabbed over. E, F, and G are tabbed over. E has 2 children, I and J. And then J has 2 children, O and P. And notice the only things that have children are folders, because folders can't, like files can't have children. Okay? See how that actually works? So that you can do this recursively. This is one way to do it. I would reckon that it's not the best way because it's asymmetrical, but it would work. Okay? And it would work for any structure that has an undefinable number of children to begin with. If you create another file, it just goes right into this as another sibling. Okay? This works fine. All right. So that's one way to represent a tree. Another way to represent a tree, and in fact a particular type of tree that Nathan brought up earlier, is this thing called a binary tree. This is the simplification of trees. Okay? A binary tree has the limitations that you only have 2 children. We call the children left and right. Okay? A's right child is C. A's left child is B. B's left child is D. B, in this case, doesn't have a right child. C has a left child E and a right child F. And E and F are both leaves with no children. Okay? The object that you create is pretty simple. It's very similar to a linked list, except instead of having a pointer to next, you've got a pointer to left and a pointer to right. Nice. Okay? The depth of a binary tree is more normally very small. Okay? It's actually on average the square root of n, as it turns out. But it doesn't have to be. Notice, A here only has a right child, B only has a right child, C only has a right child, and D doesn't have any children. What does this look like? A tipped over linked list, right? Which means that if you have lists like this, they can be what we call degenerate trees. If you have trees like this, this is also a degenerate tree because you go right, left, right, and you don't have the benefit of anybody having 2 children. These behave like linked lists, and we don't like them. All right? We don't like them because why not just use a linked list if we're going to end up with stuff like this? So we will actually generally try fairly hard to keep the structure such that we don't end up with these. Okay? It's harder than you might think, as it turns out. Your next homework assignment is going to be on trees, binary trees, and you won't have to worry about that. Okay? We will actually put a bunch of things into your tree that make it so that it stays relatively even. Okay? But you can get these weird degenerate cases. Okay? All right. A couple more vocab things here. Binary trees, we can have a binary tree called a full binary tree. A full binary tree means every node besides the leaves has 2 children. In other words, no single children. Okay? A, 2 children. B, no children. That's OK. C, 2 children. D and E, no children. Can't have a single children in a full binary tree. Pretty simple. Contrast that to the very poorly named complete binary tree, which sounds a lot like full, if you ask me. I always get these two mixed up. A complete binary tree says here, every level except possibly the last is completely filled, and all nodes are as far left as possible. What that means is that you can fill in A as the first node. Then you have to fill in B because you have to go left to right. Then you have to fill in C. You can't jump down here because C would be not filled and it would break the completeness of this tree. D, you have to go C, then you go D, then you go E, then you go F. If you don't have any more nodes, this is still considered complete because it's filled in from left to right on the last level. Okay? We will use this when we get into other kinds of trees called heaps, which require this behavior because of how we're going to store them. It's not going to be these nodes. It's going to be a little bit different. Yeah, Boris.
Why is it as far left?
That's just by definition. We're just going to make it as far left. You could have done it as far right, but we're just going to keep everything as far left as possible and always go from left to right, just by convention. Okay? All right. Any other questions on that? Full versus complete. Okay? We can actually do some fun things with this. Remember when we did the stack, and remember when we had postfix notation? It looked like this: A, B, C times plus D, E, blah, blah, blah. And we said, whoa, that's a pretty cool way of doing calculations. And there were whole calculators based on this notation, reverse Polish notation or postfix calculators, right? You can represent postfix in a tree. Here's how it's represented, right? This times asterisk here means multiply B and C. This plus says add A plus B times C. This plus says add this side to whatever this side is. You get it? It's just a tree, binary tree. And it's binary because each operator only acts on two operands. And in this case, the operand here is whatever the solution to this is. See how that works? If we want to create this ABC postfix notation, there's a little recursive function to do this. It's called post order, which means you're going to print things out in the end. Here's what you do. You start out and you traverse left. And by traversing left, you've restarted this. OK? And then when you traverse left, you go down to whatever's left, and you traverse left. And you keep following. And then if there's nowhere to traverse left, or you're done with it, you traverse right. Then you print the node. And then you return. OK? Let's see if this works. Starting here, what's our algorithm say? Traverse left. Then we're here, and we just start over, so we traverse left. At A, can you traverse left? No, so you can't actually do it. Can you traverse right? No, so what do? Print the node. So we print A. There it is. Then we return because we've just printed it. What did we just do at the plus? Traversed left, so what do? Traverse right. What do we do here? Traverse left. Can't traverse left, can't traverse right. Print B. Boom. Return. We just traversed left, so we traverse right. Can't traverse left, can't traverse right. Print C. We return here. We did both. Return or print times. Print times. Return. We just did right, left and right. Print plus. That's the plus. We were done to go up here. We just traversed left, traverse right. You see? Then we get here, traverse left, traverse left, traverse left. The next thing we print is D. Go ahead and walk your way through this and see that this works. OK? It's a nice recursive way of getting this postfix notation out of your tree. OK? I'll let you walk through that on your own. OK? Questions on that? It's kind of neat. We will learn other different ways of traversing. You can traverse what we call in order, or pre-order, or level order, which is interesting, where you'd go plus and then plus times and then A times plus G, right? Which is actually kind of tricky to do, as it turns out. Any questions? All right, we've caught up a little bit more today. Woohoo! See you tomorrow. More tomorrow on binary trees.